Yes, I'm Hiroki Matsui from Chiba University in Japan, and I thank the organizers for inviting me to Paris. This is actually my first time to come to France, but just for this week, yeah, I have to come back to Japan quickly. Okay, and today I'd like to talk about topological full groups by many examples. Okay. So this is the overview of my talk. So I'm interested in some dynamical system on a control set. And by dynamical systems, the most fundamental example is the one comes from group actions of discrete groups on the control set by homomorphisms. But not only group actions, but also we are interested in some equivalence relations on control sets or something else. Okay. And from these dynamical systems, I construct groupoid with nice topology, which is called Etale groupoid. And for groupoids, I use this font, calligraphy G or calligraphy H or something like that. And this is something like group, but it has many units. Okay? Usually, of course, a group has a unique unit, but groupoid has many units, and they form the space of units, unit space, G0. And this space is naturally identified with this control set X. And from this Etale groupoid, okay, you can find there are three arrows. Okay, first, I can construct the groupoid C-star algebras. Okay, from a groupoid, I can construct a C-star algebra. And originally, I'm working on operator algebras, so this is my hometown. Okay, and for a C-star algebra, we can consider its k groups of a C-star algebra. So it's K0 group and K1 group. And next, I can also consider homology groups of the Etale groupoid G, which is denoted by Hn of G. And it's a natural extension of usual group homology. Okay. And this is an abelian group, infinite family of abelian groups. And the last one is topological full group, double bracket of G. And this is a subgroup of homeomorphism group on X. And this is not abelian at all, but it's a countable discrete group. And recent many studies show that these topological full groups provide us very interesting examples of discrete groups. Okay, so I'm interested in these pictures. And today, in particular, first I'd like to consider the K groups versus homology groups. Okay. They are both abelian groups, so it's natural to compare these, right? And next, well, topological full group is a discrete group, and I will explain it later. But I can define a natural map I called index map from the topological full group to H1 of G. And moreover, I can discuss the abelianization of double bracket G sub AB. This is abelianization. I can discuss this group and its connection to homology groups. So the main interest in this talk is these two things. Okay. And let's begin with the definition of Etale groupoid. What is a groupoid? Okay. And groupoid G is a group-like algebraic object, but in which the product may not be defined for all pairs. So G, an element G is thought of as an arrow from this point to that point. And these dots, these points belong to the unit space. And R denotes the range map, G inverse. This is range of this arrow. And this is a unit. So this is a point of our contour set. And this S denotes the source map. So S of G is equal to G inverse G, means this point. And it's again the point of a contour set. And my G is just an arrow on this point to that point. So they form, they represent some dynamics on a contour set. Yes, and I denote the unit space by G0. And with this algebraic structure, I also consider the topology, which fits into the algebraic structure. And such an object is called Etale groupoid, okay? It is locally compact Hausdorff space compatible with the groupoid structure. And this map, range map, and the source map must be a local homeomorphism, okay? So being local homeomorphism, this is Etaleness, okay? And in what follows, we assume always, we assume.
You mean that like the groupoid is acting on this space? That's what you mean? What do you mean it's equipped with a local?
Well, G is yes, G itself is a space, topological space.
So this is itself.
Yeah.
It's not like a
Yeah.
And in what follows, okay, I always assume the unit space is a contour set. Okay, I consider the dynamics on a contour set. And by technical reason, I assume G is essentially principal. And it's equivalent to say that the dynamics is topologically free. Okay, then for each Etale groupoid, I can associate the topological full group. Okay, this is a exact group. Okay, okay.
Could you repeat what is essential principle?
Essential principle is, well, I do not give you a precise definition, but it's equivalent to topological freeness. So the action is free on a dense open subset. Okay. And the compact open set U of G is called the G set if both the restriction of R to U and S restricted to U are injective. Okay. So U is defines a partial homeomorphism from some Kropen set on the contour set. And my topological full group, double bracket G, is defined by this. This consists of homeomorphism gamma, for which I can find a G set U such that this gamma is equal to R composed with S inverse. Right? So, well, so I can say that the gamma is that an element of the topological full group is a homeomorphism which is affiliated with our dynamical system. Okay. And the most basic example comes from, of course, a group action. Okay. So let's consider group action. So this gamma is a group, discrete group. And the phi is the action on a contour set X by homeomorphism. Then I consider this gamma times x, the product. And the topology is just a product topology. Okay, gamma is a discrete group, and x is a Cantor set. The topology is a product topology. And then it has a natural groupoid structure. So I call this by G sub phi. Phi is the name of this action. And this is a fundamental situation of the groupoid. And in this situation, what is this topological group? And the answer is quite easy, but well, gamma is in the member of this group if and only if we have a continuous map C from the Cantor set X to the group gamma, such that gamma of X is equal to phi sub C of X, right? So locally, gamma is written as some element of group, okay, locally. So this is the definition of topological Hull group. Well, so any, so yeah. So okay, so in this slide, I'm saying that if I'm given Etale groupoid, then I can construct a topological Hull group, okay. And the most fundamental example which I have to keep in my mind is the group action. Okay? And I'd like to go to some other examples later. Yes. And next, we have to keep this theorem in our mind. So for minimal groupoids G1 and G2, so minimality is clearly minimality is naturally defined for groupoids, and of course, a groupoid is minimal if and only if the dynamics is minimal. Okay, and then these conditions are equivalent to each other. And first, G1 is isomorphic to G2 as an Etale groupoid, as a groupoid with topology. And second, the double bracket G1, this is the topological Hull group, is isomorphic to the topological Hull group of G2 as a group, as a discrete group. Okay? And the third condition says that the capital D, which denotes the commutative subgroup, okay? Commutative subgroup is isomorphic to the commutative subgroup as a group. And the fourth condition says that there exists isomorphism between these two C-star algebras, such that pi restricted to this subalgebra is an isomorphism to this algebra. And this capital C denotes the continuous functions on the unit space, complex valued continuous functions on the unit space, and it's an abelian C-star algebra. It's a commutative C-star algebra. And this commutative C-star algebra is naturally sit in this C-star algebra as a Cartan subalgebra. Okay. So the last condition says that I can find isomorphism preserving their canonical Cartan subalgebras.
What is upper index 0?
Unit space. Yeah. Okay. So, so if we assume the condition 1, then clearly the other conditions follows. Okay. And it's a good point to know that yes, these conditions 2 or 3 imply 1. So this means that our topological Hull group or its commutator remembers the Etale groupoid. So, well, in general, well, if I'm given two discrete infinite groups, it's not so easy question to if they are isomorphic or not, right? Yes. But in this situation, it may be possible to distinguish them by using information from dynamical systems. Okay? So let us remember. So Etale groupoids are isomorphic if and only if as associated topological Hu groups are isomorphic. That's if and only if condition.
This is your theorem?
Yes, yeah, more or less, yeah. Yeah, they have much history, but
Sorry, this may be familiar to most people here, but not to me. Could you just say another word or two about the meaning of minimal?
Minimal. Yeah, so here minimality is defined for groupoids. Yeah, and I'm not saying use a precise definition, but it's exactly corresponds to the minimality of the dynamics. So each orbit is dense. Yeah. In the case of group actions, each orbit is dense. This is a definition of minimality.
Also a question. When you say isomorphism, you mean modular equivalence?
Yeah, we can say something like this statement. Yeah. Okay, so now I have explained isomorphism theorem. And next, I have to introduce the homology groups of groupoids. And again, I don't give you a precise definition, but this is the homology groups of this chain complex, where here G0, this is a unit space, and G1, this is nothing but G itself. And G2, okay, G2, what is this? This is a space of composable strings of n elements. So G2n is a subset of G times G times da 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 times G, okay? But I'm looking at only composable strings. Okay. And then, well, it's in a natural way, I can define the, boundary maps. And this is the chain complex and takes homology groups. And in the case of group actions, this nothing but the usual group homology with coefficients with the integer valued continuous functions on the unit space. Okay, this is a classical notion of group homology. And okay, let's look at this delta 1. Delta 1 is a map from this space to that space. And this CC means integer valued continuous functions with compact support, okay, compactly supported continuous functions on the groupoid G, the integer valued. And for such a function f, okay, I map this function f by delta 1 and take the value at x. X is a point of a unit space. Then the delta 1, its definition is this. Okay? So, in particular, H0 is the quotient of this by the image of delta 1, of course. So, each f is written as some sum of characteristic function of some G set. Okay? So, the image of delta 1 is generated by these functions. The characteristic function of SU minus 1 sub the range of U. And then what is H1? So H1 is the kernel of delta 1 modulo the image of delta 2, right? And what is kernel of this delta 1? So if U is a G set such that its source and range are both the unit space, then 1U is clearly belonging to the kernel, right? And such a U, from such a U, I can consider its associated element of topological Hu group. So in this one can define the index map I from the topological full group to H1. Okay. Yes. I can map the element of the topological full group by the equivalence class of this cycle, 1 sub u. Yes. Okay, so now I have introduced objects which I need, and I make two conjectures. So I'm considering essentially principal, minimal, Etale groupoid with the unit space a control set. And the first one is HK conjecture, which says there exists isomorphism between homology and K groups. Right? Homology groups of the Etale groupoids are isomorphic to the K groups of the associated C-star algebras. This is not a theorem, just a conjecture. Okay, and let's call this HK, homology K groups, right? And next one, I'd like to discuss AH. This means abelianization and homology, by which I mean there exists a short exact sequence like this. So here, I have the abelianization of the topological full group, GAB, and here I have the index map I. The index map I is the homomorphism from the topological full group to H1, but H1 is abelian, so it goes through the abelianization. And in the case of usual group homology, it's well known that the H1 is isomorphic to the abelianization, right? In the case of discrete groups. But in this case, I get some kernel. And this conjecture says that the kernel is this, H0 times Z2.
Excuse me. For the HK conjecture, you assume that there is some Chern factor that gives you the isomorphism?
Yeah, it's a stronger form. Yeah, yeah. It may be natural. There exists some natural homomorphism from here to there, and this is an isomorphism. Yeah.
But you have the character. You know how to construct the character.
No. In general, I don't know.
So if it comes from a proof action, do you know this?
No.
As a consequence of one constant?
Right.
Rationally, only after transferring by the rational.
Yeah, this clearly relates to the Baum-Kohn.
But is it a consequence or?
I don't know. Yeah. Yes. Okay, and by weak AH, I mean this sequence is exact when removed this part. Okay? And in many cases, I cannot prove AH, but I can prove weak AH. Okay? Weak AH means this is exact. Okay, then in the rest of my talks, I'm giving you many examples. Okay? The rest of the talk consists of just examples. Okay? And the first one is minimal Z actions. Okay? It's the most natural one. So let's consider minimal action of the integers on the control set. Okay, in this case, it's well known that H0 is isomorphic to K0, H1 is isomorphic to K1, and in this case, this group is isomorphic to the integers because of the minimality. And the higher Hn vanish. So, yes, HK holds. Yeah. And also, AH holds. Okay. The topological full group, its abelianization is isomorphic to the integer plus H0 times Z2. So AH also holds. And it's known that the commutator is simple. And in many cases, I can prove that this commutator is simple. Actually, in all the examples which I will explain, the commutator is simple. So it's very natural to compute this abelianization, right?
Can you explicitly say what this Z corresponds to and what are these?
This Z? This Z is this H1. Index map, the image of the index map. So the short exact sequence in the AH conjecture splits in this case. Okay. And the commutated subgroup is finitely generated if and only if phi is expansive. This is also known. And this groupoid is isomorphic to this groupoid if and only if phi 1 is conjugate to phi 2 or phi 2 inverse. This is the theorem of Boyle-Tomiyama. So the Etale groupoids are, in this case, completely classified, already classified. So they are isomorphic if and only if the topological full groups are mutually isomorphic. Right? This is a consequence of isomorphism theorem. And moreover, it's known that this is amenable. So this gives us an example of what? Amenable, simple, infinite, finitely generated group, right? Yes. And uncountably many. Okay, so this is an example of minimal Z actions. And then what is next? Next to minimal Z to N actions. It's natural. So let phi be a free minimal action of Zn on the Cantor set X and consider the associated groupoid. Or, yes, just consider this dynamics. Then, when N is 1 or 2, it's known HK holds. By a direct computation, we can show it. But it's not known in general. And as you said, by using the Chan character, we know that the HK is true after tensoring the rationals, right? The Chan character gives us isomorphism with tensor the rationals. And unfortunately, in this case, the group homology may contain torsion, so it's not clear the integral version holds or not. So I don't know. And yes, this talk contains many open ends. So many problems. And this is, yes, one of the, I think, biggest issue. Then as for AH, I don't know. But I can show weak AH holds in the case of minimal Z2N actions. So this sequence is exact. And I think this homomorphism is injective, but I cannot show. Yes, and the commutated group is known to be simple. Okay, and well, yes, moreover, yes, I can ask.
What is this other map from H0 tensor Z?
Good question. Yeah, good question. Yeah, I didn't mention it. Yes, and does not exist a clear canonical definition. But I can give you an informal definition. Okay, so take a Kropen set, and suppose this Kropen set is not so large. Then I can find another Kropen set, which are disjoint from the original Kropen set, and they have the same equivalence class in H0. Then I can define an element of topological full group by moving this Kropen set to that Kropen set, and that Kropen set to this Kropen set. This is a transposition. And this transposition belongs to the kernel of index map. So in such a way, the characteristic function on the Kropen set 1U, this is the element, this defines the equivalence class in this group, maps to an equivalence class of that transposition. Okay. So this is an informal definition. Okay, and its amenability is also a natural question, but it's not yet known. But sometimes it's amenable and sometimes not. Yes, and I didn't write it, but for example, I can ask myself that when this is finitely generated or not. Okay, so we have many questions, but I don't know the answer. Okay. So next example is then one-sided shifts of finite type. So I'm considering an irreducible finite directed graph. Okay. My graph is finite and directed. Finitely many vertices and finitely many edges. And irreducibility means that that's enough complicated. And let A be the adjacency matrix. And consider this space. This is one-sided infinite path of edges. Okay, terminal of this edge is equal to the initial vertex of this edge. So I'm considering the infinite paths of this graph. And this is the contour set. And let's consider the one-sided shift on X. And this is not a homeomorphism, so it's not the action of the integers. But this dynamics is a fundamental object in the study of symbolic dynamics, and it's called shift of finite type, SFT, shift of finite type. And when I have only one vertex and n edges, so each edge is a loop at this unique vertex, then it's called the full shift over n symbols. And we can construct an Etale groupoid in a natural way from the SFT. And I don't tell you the precise construction, but there is a natural way to construct an Etale groupoid. And its homology groups are already computed. H0 is co-kernel of this matrix acting on Z free abelian group. Okay? And H1 is kernel of this matrix. Okay, AT means, of course, A transpose. And higher homology vanish. And C-star algebra associated with this groupoid is also the famous one. It's Kunz-Krieger algebra, and whose Ki groups are already known, and they are equal. So HK holds. Okay? By a direct computation, I can show HK holds. And this triple co-kernel of this matrix, and this is equivalence class of the constant function 1 on the unit space in H0. And this determinant, it's some natural number, is a complete invariant for the isomorphic class of GA within SFT groupoids. So I know I already classified these groupoids. And the abelianization is equal to this group, H1 plus H0 tensor Z2. So AH holds, AH conjecture holds, abelianization versus homology holds. And the commutator is simple. And when next is a full shift over n symbols, that is, our graph has unique vertex and n loops, and this topological full group is canonically isomorphic to the classical Higman-Thompson group Vn. Okay? And in the same way as the Higman-Thompson group Vn, I can show this topological full group is of type F infinity, in particular finitely represented. And moreover, this has the Hörger property. And clearly, this group contains a free group, so it's not amenable. But it's amenable in a weak sense. Okay, so far I have discussed relatively old results. Okay. So now I'm going to relatively new computation. So first, I'd like to consider products of SFT. So in the previous slides, I considered shift of finite type, SFT groupoid. And I take the product groupoids, GA1 times GA2 and then GAM, right? And the product of groupoids corresponds to product of dynamical systems. Okay? Then, first, I prove that these two groupoids are isomorphic if and only if the number of product components equal, and after permutation of indices, each summand has almost the same invariant. Okay? Co-kernel and determinant, they were complete invariant for the isomorphic class of this single SFT groupoid. Okay? So for each coordinate, they have to isomorphic. And the last condition says that the position of the constant function 1 are the same. Okay. And it's clear that if G1 is isomorphic to G2, then these conditions hold. No, the converse is clear. Yes, but yeah, I can show that if they are isomorphic, then I can show these conditions. So I completely classified this class of Etale groupoids. So this gives a new topological Hu groups, countable discrete group. Okay, so they are new toys. And as for homology, it's possible to prove that, okay, so let's consider some Etale groupoid H and SFT groupoid GA and consider its product and consider its homology groups. And then I can prove that this isomorphism, which is something like a Kines formula, right? Yes, HP and H0 and HP minus 1 and H1 plus Tor group, right? It's a kind of Kines formula. And I think in general, general H and general G, there should exist some Kines formula, probably, like a group case, like the case of discrete group homology, but I don't know because, yeah, it's a bit difficult problem because when I was a student, I didn't take the course of homological algebra. So, yeah, so this is also an open end. So, please try. So, in particular, if HK holds for this H, then HK also follows this product. Because as for the K groups of the C-star algebra, I have already known, its Kines theorem is already known. And in this case, we can verify weak AH, but it's not clear if AH is true or not. And as a special case, I can consider the product of full shifts over n symbols. And this case, the topological Hu group is known as a higher dimensional Thompson group, denoted by KVN and studied by Brin and other people. So in the case of 2V3, our control set is like a square, unit interval times unit interval. And I divide 3 equal pieces in each time. And yes, transformation is given like this. So for example, this rectangular A goes to this rectangular. So for the horizontal direction, I keep the size. But the vertical direction, I shorten the length by 1/3. So this forms some group And it's a higher dimensional version of Higman-Thompson. And it's denoted by 2v3. And some people working in this class of groups. And yes, and my setting includes the study. Yes, okay, so yeah. So next, let us consider another generalization of the classical Higman-Thompson. It was considered by Stein, Melanie Stein. So let P be the multiplicative subgroup freely generated by these natural numbers. So P is, as a group, P is just a free abelian group of rank K. And let A be this ring. Then Stein's group, VRAP, consists of right continuous bijections of this half-open interval, which are piecewise linear, with finitely many discontinuities and singularities, all in A. Okay, so the capital A is a set of these discontinuities and singularities. And slopes, okay, slopes are in P, this multiplicative group. And mapping this this set to itself. So obviously this is a generalization of the classical Higman-Thompson. Well, P is generated by only one natural number n. This is V and R. Okay? And Stein proved this is again of type F infinity. So in particular, it's finitely represented. And moreover, she proved commutator is simple, and she computed abelianization. And as for this group, I can say this comes from some Etale groupoid in a natural way. So this is again a topological full group. And as for this topological full group, Etale groupoid, I can compute its H0 is ZD and H1 is ZD to K minus 1. And D is GCD of these numbers. And, but I have not yet computed the higher homology. So, okay, this is also, again, open problems. So in particular, AH conjecture, abelianization conjecture is true because this coincides with Stein's result, Stein's computation of abelianization. And I have not yet known HK. And if I'm given two groupoids, Stein groupoids, P and Q, P is generated by these natural numbers, Q is generated by these natural numbers, and if G is isomorphic to H as an Etale groupoid, then I can show K must be equal to L, and also this is equal to this. Okay. So in particular, when P is generated by 2 and 3, and Q is generated by 2 and 5, in this case, their homology groups are trivial, so I cannot distinguish them by looking at homology. But this thanks to this theorem, they are not isomorphic. Okay. Yeah. And yes, and also clearly considered its generalization, and it involved some irrational slopes. Okay, and in this case, well, I don't know for general irrational numbers, but if beta satisfies these equations, I computed homology like this, and as a consequence, HK holds, and also AH holds for this dynamics. Okay, thank you.
Let's take two one-sided shifts of finite type. Suppose that the logical groups are isomorphic. My question is, what can you say about those systems? In other words, does exist a version of the Boyle-Kamiyama theorem of Topological?
Yeah. What I can say is that they are continuously orbit equivalent. Yeah. No. Yeah.
So, is there anything of this kind for higher dimensional Kunz-Krieger algebras and correspondent multi-sided shifts?
No. The multi-dimensional shift is a much hard object. It's completely different from my situation.
Yeah, but it's still, can you?
Yeah, it's interesting to consider, multi-dimensional shift.
But nothing is more.
No.
Can you characterize the sample for the topological group generated by Cleary
Yeah. So it's natural to expect that this is equal to the kernel of the index.
Is that in the kernel?
Yeah.